millions of pieces, right? So how a metals to metal should not get shorted, how the physically thing. So all the physical characteristics of the design is mentioned in the PDK. So one such file, they call it as a technology file. The technology file will say that, hey, in this design, you can use, like, let's say 10 to 12 metal layers and you can complete your design. So 10 to 12 metal layers, they categorize that low metal layer is used for basically connectivity at the lower level, gate level, which means drain source at the transistor level, they connect it through the lower metal layers. And higher metal layer, they connect it to the external world. So external world is basically, you have some interfaces, you have some power connected, all the things will come from the high metal layer. So why do they segregate this? The reason is the low metal layer always have a high resistance. Okay, if you see the technology file in any library, right? So the low metal layer will have high resistance, whereas high metal layer have low resistance. So when you design power, you need to obviously design using the high power so that you get a less resistance, right? So all these will be pretty confusing, but put together, right, the physical information of the particular metal is present in the PDK file. That is, we call it that as a technology file, right? And there is two more information. One is library. So the technology library they call. So what is library? So you know that every chip is having a component. For example, you have a flip-flop, you have an AND gate, buffer kind of things, right? So what do you do with that? Let's say I'm designing a flop and I'm designing a buffer, I'm designing an AND gate connected through other flop. So what I'm going to do with this, right? So basically, when you clock them, right? When you clock them, you are expected to meet the timing between the two flops. Then only the data can be captured from the launch to the capture flop correctly, right? Which means the performance of the design is basically the timing point of view. So the timing is the second most important in design, starting from synthesis, right? What is timing? Timing is nothing but if you have a component, if a data is passing through that component, the time taken for the data from the start point to end point is called the delay, right? So this is called as delay. So each and every component will have a delay, let's say 30 picosecond or something like that. So how does it matter for the library, right? Suppose I'm going to take 22 nanometer process, and AND gate will have some delay value, right? It's not a single value. So in the library, they'll have a table format. The table will have input transition and output load, because AND gate will be there, but the output can be connected to multiple ranges. Similarly, input can be connected from anywhere else. We don't know how much is coming. So they will also have a range. So the library will be characterized in such a way that for this particular output load and for this particular input transition, the AND gate will take 30 picosecond delay, right? So this is how the library is characterized by the process guys, and they'll give this information. So literally, we don't need to know all this, but we need to understand this so that you know how the timing is calculated by the tool, right? That's why I'm putting more efforts and telling this. Once we see that in the library format, you will understand better, okay? So that's the predominant thing in the library. Next thing is LEF. So LEF, we will talk more about when we talk about the PNR session tomorrow, okay? So I'll move on to the slides. Before that, any questions? Okay, we'll go through. Great. So today's session, I'm going to cover most likely the flow perspective of the synthesis. Now I explained that what is going to happen in synthesis. So we are just going to translate the RTL to gate level, right? So what is synthesis doing with respect to the tool, right? Because industry standard tool is there. How the tool is going to convert the RTL to gate level is what today we are going to see. So just put a course agenda here that we know what is synthesis foundation, and how do we set the environment for that particular synthesis to happen, and what are the core commands. So everything is working based on a tickle commands. We call it as tool command language, right? So tickle commands, and what is constraint, and how do you optimize, what is optimization, and scripting and automation, right? So these are the primary agenda which we are going to talk today. So I'll spend some like about 20-25 minutes on this, and then we'll see how we can load the tool and implement and see it how it is taking, right? So as I mentioned, right, so I'll just keep this slide. You have the definition here, right? So synthesis automated process of converting high level RTL, which is register transfer level, because you are going to transfer data between the registers. So basically it's converting high level RTL code into optimized gate level netlist. So this process is called as VLSI synthesis, right? So basically, this acts as a bridge between the front end and back end in the industries, right? So you can see the key transformation here. So basically, human readable. You can read that Verilog file and you can understand, and it will basically map to the technology specified standard cell. Standard cell is what I'm talking about, the logic gates and flop. Why it is called standard? Because all the process guys give you that. So it's a standard way of having the cells. So standard cells, right? So how are you going to do the synthesis, right? So with the help of EDA vendors. So primary vendors, we have Synopsys, Cadence, and Mentor Graphics, which is Siemens now. So, and among them, Cadence is pretty famous and used by many industry folks here, and it is pretty easy, very friendly also. So, and Cadence Genus is called the synthesis tool here, right? And basically we chose Genus because it is yielding good timing, power, and area numbers compared to other industry tools, right? And other reasons are they have many optimization techniques. So optimization, we will look what is optimization, how it is directly linking to your digital electronic subjects in the upcoming slides, right? So, and flow. So industry flow is basically, you can see, so the RTL input. So you have an idea, the architecture, the front end folks basically design you an RTL and give you the name, something called as .v or .sv file. That is your design. Let's say I'm going to design a counter. The front end guy will give you a file called counter.v or counter.sv. So that is called as RTL input, right? The format can be Verilog or VHDL design files. The corresponding test benches. So test benches, as I said, you need to verify the RTL, right? So for the verification purpose, they give the test benches also, so that verification folks can verify and make sure that RTL is totally fine, right? Next step is setting up and reading. What do you need to set up? So the PDK from the process, right? They have a lot of information. So you need to set a particular environment in such a way that what all you need, you just read alone, right? So to setting up that, we have library configuration and design file reading. So all the physical related things. The next step is basically elaborate. As I said, the RTL will have many hierarchies, right? Many modules and many hierarchies. So the tool will read each and every Verilog file. It's not a single Verilog file in the industry. For example, say I said counter.v, but if I say some architecture.v, within architecture we'll have SRAM.v and memory.v, non-volatile memory flash.v, and we have ALU.v. So multiple Verilog files will be there. So the tool will next step will do elaborate the design. So elaborate is basically, again, it will check for the syntax error. It will check for whether hierarchical connection is proper or not. So elaborating the entire design it will do, and make sure that it will understand the design. It will understand the Verilog code that, hey, this is a flop, this is an AND gate, this is an OR gate, this is a combinational circuit, right? It will understand. Okay. Suppose if it cannot understand a logic, right? Suppose it cannot understand that, hey, this logic is there, but I don't know what logic is this. Any logic need to be there, which is there in the library, which means it has to be AND gate, OR gate, XOR, whatever the basic gates or the combination or sequential. Apart from that, if something is there, if the tool cannot understand, this elaborate will fail, saying that, hey, there is some issue with the circuit, go and change it, right? So that is the secondary step in elaborate. So next step is an important step, which is constraint. So what is constraints? So constraint is an important subject. You are going to design a chip, let's say Snapdragon processor, right? Snapdragon works with 2.5 gigahertz, right? So which means my frequency is 2.5 gigahertz. So the constraint, you need to mention that the clock frequency is 2.5 gigahertz. Similarly, I need to close this with this much area only. So I need, because area increase is yield increase. Yield increase is manufacturing cost increase. So area is also important, right? Power. So power is basically, if everybody wants the phone to be charged almost quickly, and it should not drain quickly. That is current generation. We know the importance of the phone, right? So how do you take care of power? The power dissipation should not be more, and the power, how do you take care of the power? So this is the constraint where you define that how much frequency your chip is going to work, and how much power is allowed to dissipate, or how much area you wanted to check. So these are all comes under the constraints part, right? So then once all the things are done, then you are going to do a synthesize command, right? So see, the tool wise, it is just synthesize. You are just going to type synthesize and put enter. But you guys need to understand what it is going to do, right? So synthesize, basically they have two-step synthesis here. So one is a generic step, another one is technology step. So what is generic? So generic is, we'll see in the upcoming slide, what is generic and what is technology, right? So once synthesis is done, your RTL is converted to gate level netlist. So your RTL will have always at POSH kind of thing, whereas your gate level will have the D flip-flop name and connections in the netlist. So that is RTL to gate level. Then you do, once the mapping is done, you go for optimization, because you gave the constraint, right? I need to work with this frequency, right? So the tool will work on optimization. So once the optimization is done, you then write out the gate level netlist. So the output of the synthesis is gate level netlist, which will be taken care by the physical design folks. Okay, so these are the overview of the flow. So we'll just get through quickly what are the steps, right? So setting up the design environment. So what are the things? So we need, what are the software requirements we need for the tool to run, for a bigger designs or a medium design. So we need latest version of the tool, of course, the GNS latest version, and we need a valid license server configuration, because if there is any update from the vendor, right, we need to get that. So we need to have valid license server, and obviously Linux or Unix operating system. So the preferred is RHEL and CentOS. So these are all related to operating system, because the machine is very important for a tool to run. You cannot run in a random Windows machine, it will crash. So it has a separate, and we need a minimum of 16 GB RAM and 64 GB hard drive, right? Recommended for larger designs, right? So we need to understand these configurations very much, so that when you install something in your, let's say in your laboratory also, you need to take care of this, right? And next one is design files. So design file is basically, as I said, is RTL source files, which is .v, and technology files, .lib from process, which I explained, and SDC file is constraints file. SDC is synopsis design constraints, right? SDC. The design constraints, we'll get through it in the last slide, what is going to be there in the file. And how do you configure the flow, file and scripts? Because if you plan to run anything, you need to have some flow, methodology, and then scripts corresponding to that, so that your run can be easily done, right? The directory structure. So usually, if you are working on some project, usually we follow this directory structure. Let's say you are going to work on a project, you have a project directory structure. Within the project directory structure, you will have the primary thing, RTL. So inside the RTL folder, you will have .v, .sv and everything, right? And .libs, you have .libs, where the product, as I said, the manufacturing guys gives us, right? And scripts is how you are going to do the synthesis. You can have a scriptable format. It can be a single tickle file, or it can be a multiple tickle file, all script file, right? And constraints file, where you are going to create the clock, which is needed for timing. You are going to set the constraints for area and power, right? And finally, the outputs. After the synthesis, what all the data I need to take it to the backend. So that will come under the output. So these are the primary directory structure, which we will follow in synthesis, right? Yes. The important thing, right? So see, the flow wise, only 6 commands you are going to run it, right? If you run the 6 command, you can randomly convert any RTL to gate level, right? So, but one need to understand that if you are working on synthesis, you need to understand certain requirements, how we should not code, how we should code the RTL, right? So those understanding are very much needed for synthesis engineers, right? So that's why I added this specifically, that you have a design input requirements. How do you code it, right? So here, one of the quality checks, important thing is, we need to use only the constructs. So how many of you are familiar with constructs here? Verilog constructs, right? So you need to read about Verilog constructs. Then only you know how I code it, right? So we need to use only synthesizable constructs, which means you should avoid delays, initial blocks, simulation code only, right? So that is the first important point. Second one is clean coding style, which means you need to have a proper naming convention. Suppose if you are working on memory, you need to put that this is a memory, and you need to differentiate between volatile and non-volatile memory. Or if you're working on an architecture, if you're working on a flip-flop or a synchronizer, you need to give that name particularly, right? Otherwise, we don't know what is this logic about, what is this hierarchy. So clean naming style should be followed. right? No latches. So why no latches? How many of you know the difference between latch and flip flop here? Answer, please. Right. Gets triggered. Perfect. So why we are not using latches here? You have any idea that here I'm saying that no latches. So do you know why? Why instead of latch we are using flip flop? Does flip flop contain latch? Yes. How many latch? Two latch. Okay. So master and slave latch, right? So why the latch is not being used for a timing? The timing analysis of a latch is very tough, right? Why? The reason is at the flip flop you are going to launch a signal at rise edge, right? And you are going to capture at the next rise edge, which means rise, fall, rise, right? Let's take if you are taking a latch, right? Latch is level sensitive, so data can be launched at the level wherever the level is starting. It can be captured at any level. The level is so big, right? For example, you have a 0, 5, 10 as a clock period. 0 to 5 the data can be launched, but between 10 to 15 anywhere the data can be captured in the latch, right? Edge is a single edge, whereas the latch is basically half of your timing cycle. So the latch timing analysis is very complex in industry. So that's why we avoid the latches unless it is, it is preferred for some multi-clock domains. We use latches. I'll tell about later how do we use latches in clock gating and all. But generally, replacing the flop, we don't use latches, right? Basically, for now you understand that there is a timing analysis complexity. You don't use latches, right? So next one is parameterization. So that is basically you use parameters, right? Basically, you know about parameters. I'm using it for easiness of understanding the Verilog. I use certain parameters like A or B to differentiate between the comparator and differential logic, something like that. Right? Parameterization is always easy in any language, not just Verilog. So it is for flexibility and reusability, right? You can use the same parameter for next design. So you can create a common parameters for something which you can use in the derivative design or any other design, right? So next one is essential constraint file. So there is an industry standard format how the constraint should be, right? So one has to follow that, and basically important things are we need to have create clocks and we need to have the interface IO, how the IO part should time, power constraints and area constraints, right? Power intent, I'll skip now because it will be too much for you guys. Power intent is for low power design. So how do you take care of multi-power domain? So in a single chip, one can work with 0.9 volt, another can work with 0.6 volt, another can work with 1.3 volt. So how do we do that? We use something called as unified power format, or there is another one called as cadence power format. We use that and define the strategy and work on it. For what purpose we use this? If every chip works on 1.6 volt, right, it is going to consume a lot of power. Whereas if some of the chip are not required, we work in the low voltage, we are going to save some power. So that is the purpose of power UPF. So we use UPF to basically low power designs, right? So Genus tool. So coming back to this Genus tool, which you are going to use to do the synthesis, right? So what are the architecture, how it is going to work on it, right? So basically the first thing is analysis engine. So what does the tool does internally? Nobody knows. You are just going to type some command like analyze. That's it. Right? Internally, what it is happening, one needs to understand. Then only you know, okay, tool is doing this and tool is doing that. So basically, it parses the RTL, which you are getting from the front-end design engineer, and it performs the syntax checking, right? And once the syntax is clean, right, it starts building the internal design representation. It will have its own format to build. Suppose, let's say you have an ALU or adder circuit, it will try to build its own design internally, right? And it will have multi-language support, which means you can use Verilog, VSDL together and do an analysis. So it can support it, right? And even if you have thousands of hierarchies, the tool will able to pass each one through a pipelining methodology, right? So analysis is basically analyzing the quality of RTL which you receive, right? The next one is mapping engine, where you give the technology information to the tool, and tool will basically map. I'm going to consider a function of OR gate here. OR gate is defined. Which OR gate I need to take? The technology library will have many OR gates, right? So you know how many adders you guys know? How many types of adders you guys know? In the digital electronics you might have studied, right? So how many, can you name some two? Ripple carry look ahead, right? And a full ladder. Let's take all the functionality of this is same, right? 4-bit full adder, carry look ahead adder, ripple carry adder. All the if I'm going to give two numbers, it's going to add and give it. But what is the difference? One is better in area, one is better in power, right? And one is better in performance, right? Which means one will have consider big, size is big, performance is big, power is less. Another one is size is small, performance is medium, and like that, right? So as a VLSI engineer at the back end, so the tool does a mapping, like which one is useful for my design and my constraints, and it will map accordingly, right? Mapping is basically mapping whatever available in the technology and put it in. Suppose if I have an OR gate, it will just map some random OR gate and put it. If it is a flop, map a random flop and put it, right? So target library, it will done. That's it. Next stage, optimization engine, right? So here we have an optimization engine. So what it will do? So in the digital electronics, you might have studied about SOP and POS, right? Sum of products and products of sum. So you might have thinking, what is this equation I'm going to? They will ask you in the questions, right? You bring down this equation and solve this and get it down to 2 or something like that, right? So why do we do that? The reason is for optimization, right? The reason is you have a big circuit. The circuit may be big, but the equation you can always optimize using canonical form, right? If you do that, what happens? My entire big chip is going to reduce its area, which means you are going to reduce the power, right? So that is the optimization which the tool does here, that it will go through all the sum of product equation, and there are two methods optimization. Name that method. Remember that method for optimizations. Boolean optimization. K-map. One more. Queen-McCluskey. That is right. So these two are the algorithms which are feeded into the tool, right? Not just these two, we have additional also. So they will be doing the optimization like millions of times within just a nanosecond time, right? And then try to give you an optimized gate which is needed for your particular design. So this is coming under the optimization engine, right? The next one is basically the timing engine. So timing engine is important because you need to meet the frequency, right? So in the digital, in the flop, you might have studied about setup time, hold time, right? Everybody, yes, setup, hold, understand, right? So what will happen? What will happen to the flop if you have the setup and hold time violation? Correct. So what will happen? Suppose you have a setup violation or you have a hold violation. What will happen? You can't determine. So the flop will go to the metastable state. If the flop is going to a metastable state, then your functionality is crippled there. So entire chip is gone, right? So you will have a racing condition. They call it as race condition. So which means your entire functionality of designing chip is gone. So that is why we need to have a design in such a way that we don't have any setup and hold violations in the design. So to check that setup and hold violations, we have something called as timing engine, right? Timing engine will analyze the path. Like you said, there will be millions of paths. It will do each ridge to ridge path. It will analyze and give you what is setup and what is hold. If both are good, then your design is good. If both are bad, you need to see what went wrong, right? So that is the timing engine's work, right? So getting into the command prospects, now you understand the basics of how synthesis works, right? So just to give you what is the basic commands which we use here in the Genus tool. The reason why I'm giving more time in this is while doing it will be easier for you. You can just type the command because that is going to just take 10 minutes for you guys, right? So this is the read HDL, right? So what is HDL? Hardware description language. So I'm going to see this command syntax is just read HDL, and you can give the hyphen format name like SV system verilog, and give that name file.v. So .v may be the extension, but the format can be system verilog, right? Similarly, you have VHDL file and you have file list. Suppose you have n number of RTL files which you received from the design, you will have read HDL -f file list.f. You can give the entire file in the list format, right? So options Options in the sense, in the tickle command, while giving read HDL, what are the switch you have to use? So you have system verilog, VHDL, F, file, normal file, define, and library. So define is, in the RTL, they have something called as define, which can be a global one. Suppose I'm going to define some parameters, as I said, right? Those parameters can be defined earlier. It can be applicable for any number of designs which is repeated, right? And finally, the hyphen library. What target library I'm going to use in this particular design, right? So best practices. So you need to understand that, let's say you have hundreds of RTL files. So which order you need to read the RTL file? You need to understand that. You cannot randomly, suppose I have a top design, name as top, and within the top I have like n number of modules, like let's say 10 modules, right? And each module have a separate .v file, and I have a full chip which is top.v also. How should I read the design? We need to understand that, right? So read order is specifically matters here. So you need to add a dependency order. So we need to use module level first with the lower level, and then end with the higher level always. Then only your final RTL will be a top module. The tool is able to link the top to the corresponding all the module level which is below that. So you always go via bottom up approach. Okay, so we need to understand that point. And while reading, we need to understand that any errors are coming or not in the tool. Okay, and this is an example here which I provided here. You can see that read HDL hyphen design files .f and define sim mode equal to 0, which means this define is parameter, as I said, right? So sim mode is 0 means it's not simulation mode. So simulation mode means some verilog is there, whereas not simulation mode, some verilog files will not be taken. So that is like an if-else statement kind of thing where you can define a parameter, right? So this is how the tool reads the HDL while you start the synthesis, right? Library setup. So the next important thing is from PDK, library setup, right? So what is the library here? So we give something called as a setDB. You can see setDB is set database basically, and I'm going to do the init library search path. So how do you initially set up the library path is called as init library, right? So we give that, okay, hey, you are just setting this, you are not doing anything. You are just setting that my init lib search path is this one, which means I'm going to use this init lib search path variable in the upcoming scripts so that this is a global one, right? For example, if I'm going to receive some libraries from technology guys, right, that is called a standard cell, as I explained before. So you can see that libs, standard cell, lib. Similarly, we have memories, right? Memories will be always separate. Standard cell are different, memory is different. So you have memories.lib. The search path is this, which means after this lib, you will have multiple files within the library folder. Similarly for the memory also, right? And this is set path. Now what you are going to do is read technology library. Fast, typical, and slow. A same AND gate can behave differently in different conditions. So that we call it as PVT conditions. So PVT is basically process, voltage, and temperature, right? Why? The reason is when I increase the voltage, what happens to your gate? Your performance increase, which means my gate will work faster. So the transition time is faster. If I slow my voltage, which means lower down my voltage, the performance of the gate or the logic gate will be lesser, which means the delay will be lesser. Delay will be more, not lesser. So performance will be lesser, delay will be more, right? So why do we need this fast, slow, and typical in the industry is, so you are going to manufacturing a chip, right? So it needs to work on extreme conditions within all the world. I'm going to ship it to Canada or US, and there the temperature is not as same as Chennai, right? So you need to consider the temperature range. All the temperature, the ship should not fail, because you know that temperature is related to resistance, correct? And all we are going to work with metals, capacitance. So RC is depending on the temperature. So obviously the temperature variations will have an effect in this. So one need to consider temperature. Similarly, processes, if something is slowed down, when I do a manufacturing stuff, right, I'm going to manufacturing a chip. So there are a lot of instruments which are going to, for example, you might have studied about this UV rays passing through and etching process and all while manufacturing. So all these can induce certain effects, which is called as process. So the chip can either become slow, or it can become very fast. Both should not happen. So for that, we are having two extreme corners as slow and fast. So that is on the slow and fast. And typical is a nominal one. Suppose if I am designing something here, it works at just 25 degrees in nominal 25 degrees, right? So that is on the technology library. So generally we have like in the current industries, we have about 20 types of libraries, right? I'm just giving you three here. In the industries, we use 20 types of libraries. So you can think about the complexity. Each of the 20 library analysis, along with the corners, you need to do timing analysis for almost 200 corners, right? For one chip, you need to basically do 200 corner analysis, not just one single run, right? I need to take slow voltage, slow process, higher temperature, slow voltage, fast process, lower temperature. So you can do the permutation and combination. In all the cases, you should not have setup and hold violations. That is the industry thing. So the synthesis is directly related to the static timing analysis, which you are going to do at the end of the PD, right? And we need to understand the basics of this. So what is PVT? What is the corner? And we will talk about it more when we have the next TA session, right? And operating conditions. Operating condition is what I'm saying now, that I'm going to operate at high voltage, lower temperature. Synthesis is always worst case. You are not going to check hold on this. We will check only setup. So we just give that operating conditions here on this, right? So next, you set the now you set the environment and you set the libraries. Everything is clean. Now you are just going to do the elaborate, right? So elaborate, the command is just elaborate whatever the design name. Our design name is top, so elaborate design top. Or elaborate just top. That's it, right? And if you have some parameters, you need to define, or if you have some architecture, you need to define that, right? It's a straightforward one. So basically, it will what it will do is it will again build the hierarchy within itself. And it basically resolves module instantiation. What is module instantiation? Suppose I'm having an adder, and that adder is being used in all the modules, right? I'll have only one adder.v. So this adder.v will be instantiated in all the modules so that it is multiply instantiated. The tool will understand that this is an adder only, but the same adder is being used in multiple modules, right? So this will be taken care by elaboration. It will make sure that it will put a name, right? Module A underscore adder, module B underscore adder, to avoid unification issues, right? So it will create an in-memory representation which is ready for synthesis, which means it will create a prototype of elaborated netlist, and it will be ready for synthesis, right? So what all necessary in this what do you call elaborate is basically the design name. We need to have the proper top name, otherwise the elaborate will fail, right? The next one is parameter, architecture, and update. Suppose if you are using parameters, you need to specify the correct parameters. Is verified. Otherwise, the tool will take random parameters and work on it, and it will fail, right? Similarly, architecture, you need to do VHDL means VHDL only. Verilog means Verilog only, not change that, right? Similarly, if you are doing some changes in the Verilog file and if you want to update, you need to do update. So it will do the re-elaboration after the design changes automatically, right? So post-elaboration, what do you check? We will do hierarchical verification to make sure that, hey, my design has 100 hierarchies, all the hundreds are coming correctly after elaboration. And then check for warnings and errors in the tool. It may say something that, hey, I have an undriven net here, I have multi-driven net here, something like that, which needs to be reviewed, right? And confirm parameters values. Whatever you give no sim is applied correctly and taken or not. Okay. Done. So elaboration is done. The final part before the compile, or the what do you call is basically the gate level optimization, right? It's called as constraints, as I said. So everything is working on clocks. So how do you define the clock, right? So in the constraints file, as I mentioned, that you will have a file called SDC. So in the SDC file, you will have something called as create clock. So the create clock is a command to basically create the actual clock whose frequency the tool is going to run, right? So the name -name you can give any other name like CLK or functional or something like that, right? Period, as you all know, the clock period, which is 10 nanosecond, right? And where the clock is going to get created, it's at the get ports clock. At the clock port, I'm going to create a clock, right? So get ports clock. What is set clock uncertainty? So anybody know about what is this set clock uncertainty 0.5? Anybody can guess what is set clock uncertainty? MTech students, what is set clock uncertainty? Correct, absolutely. So ideally, clock is like straight, like you will have a straight line as a pulse. But practically, that is not possible due to various reasons I explained, right? The clock will never come straight, rise edge or fall edge. So you will have something like this. You will have a rise time, you will have a fall time, and again rise time and fall time. So this is basically the related to the clock period. But let's say you are timing the clock at zero, starting is zero, and then your period, let's say we take a 10, right? 10 is your period. You cannot be sure that it will come at 10. The next rise edge will exactly come at 10. We don't know that because there is a jitter, right? Because in the clock we have some random variations. So we are telling the tool that uncertainty of zero point 0.5 means the clock can either come at 9.5 or it can come at 10.5. So both the cases we need to analyze and fix correctly. For example, setup time, if 9.5 we need to meet, instead of 10 picosecond we need to meet at 9.5. Similarly for hold, instead of 10.10 we need to meet at 10.5, right? So this is called as clock uncertainty. This is very much important when you work on PD and other stuff, right? So set clock uncertainty is this, and set clock transition. As I said, transition is basically not zero. We are going to have rise time and fall time. We are going to have some 0.1 there. So which means you can expect a 0.1, which means in a particular pulse, you can have a 0.2 reduction. So that is called as set transition, right? And what does this do? So we define the primary clock and we define the uncertainties and transition time. So this is the predominant. So when you do this, what happens? All your flip-flop to flip-flop paths will be timed automatically with this command, right? If you have thousands of flops in design, all the flops will be automatically timed with this command, right? Now, what is left out? Where you miss the timing. So the input port to register is missing, the register to output ports is missing, input to output port is missing, right? That is another possibility. There are only three possibilities. The timing endpoint is always output ports or flop. Similarly, start points is always input ports or flop. So we are left with only now input paths. So we call them as input output paths. So for that, what we do something called as input output delays. So we said that set input delay max 2.0 and the clock, whatever the clock you defined, and all inputs, which means if you have 10 or 100 inputs in your design, for all the 100 inputs, I'm going to assign 2 nanosecond or 2 picosecond, whatever the SI unit is. That will be the output delay. So what is that output delay? 2ns. Why do we need 2ns? So I'll just quickly explain the board if you have some marker. I'll explain. Sorry, because I cannot explain that without showing that. That's why. Is this visible to everyone? Or I'll put on the top. I'll put on the top. Little big. Is it visible? Or should I draw bigger? Okay, I'll draw bigger. Sorry. That's it. Okay, that's fine. Okay, thank you. Okay. This is, let's say, chip 1, right? In this chip 1, what we have some input port, right? And that is going to a flip flop, and this flip flop is connected to another flip flop through some combinational logic, right? And this flip flop is going to an output port, right? So when you do a create clock, obviously this path, we call it as reg to reg, will be timed automatically, right? Now when you want to time input to reg and reg to output, so how do you do it? So how do they arrive at the input? The expectation is, outside the chip, you need to consider that this is going to another flop, right? And similarly, this is coming from another flop, right? And this delay, what do you call? We need to assume that, right? So industry standard is, they assume that 60% will sit outside, which means if your clock is 10 nanosecond, 60 picosecond, which means 6 ns is here, 4 ns is here. Similarly, 4 ns is here, 6 ns is here. So the set input delay is basically that, hey, I'm saying that assume that there is a delay of 6 ns at this input port when you time this path from input port to register, right? Similarly, set output delay is, hey, consider that output I'm having 6 ns, consider that. So when you do the timing analysis part, the combinational delay will be adding these two together. Okay, so that is the set input and output delays. Okay, clear? Any doubts on this? Why we use set input and output delay? Right, so this is the industry standard. So we use 60-40 generally, but it may vary, right? It can be 70-30, or it is variable. But just to understand the concept, why we have, and say there will be other path also, like you have input to output direct path. So this is called as feed through path. So there is no setup or hold time is going to come here because there is no flop associated to it. Is it true? Is it true or false? Why? So the feed through also may have an outside flop sitting here, right? And we may have an outside flop. So this is still a flop to flop path, correct? So the designer has to say that, hey, where this port is connected to. If it is connected to the flop and if the other port is also connected to flop, this is again a flop to flop. We need to meet the timing for this, right? If you don't meet it, it will go to metastable state, right? So these are the 4 critical timing parts which synthesis guy needs to understand and debug and fix them. So that is the task for this, right? Sorry. Okay, we'll move to slides. Okay, right, thank you. Right, so after the 2 primary constraints, we have something called as environmental constraints. So what is environmental constraints? So we have, as I said, we have power and area requirements also. So we have to set that, hey, my set max area is 50,000 micron or 50,000 millimeter square or something, right? So your area is restricted to that. Similarly, we have driving load, right? For all load, it should not be more than 5 femtofarad or 5 picofarad, whichever is unit, right? I'm telling the tool that, hey, my load should not be more than 5 picofarad. So what will the tool do? If something is connected to, let's say, 100 cells, the tool will optimize it and make that 100 cells to 20 cells or 15 cells connected through a buffers or something. So it will do a fan out, high fan out buffering, right? So to address that issue, we give set loads here. Don't be overloading the design so that your design is bloated. So set load is one. Set driving cell, I will not go into now. We'll skip it and we'll look at it later, right? So coming to the mapping. So now you did all constraints part and everything is done. So now you have mapping. So what is mapping? We, as I said, we do 2-phase mapping here. So the phase 1 is basically technology independent optimization, right? What is technology independent? It is just technology will have various flavors, as I said, AND gate or OR gate. But first phase of mapping, it doesn't look technology itself. It will just look at the code and it will say that, hey, it is an OR gate. It will just map to a random OR gate, which is called as GTech cells. It will not have any technology dependent. Just a GTech OR gate, it will map. Similarly, GTech flop, something like that. So they just focus on logic minimization and structural optimization here at the phase 1, right? The phase 2 is basically the technology mapping. Now you have the library which is provided by the manufacturing guys. The tool will go into the library and see which is the optimal gate I need to choose. And it has the flexibility to do that, and it will do, and it will give a name. At that time, whatever the cell name which is present in the library will be used instead of GTech. So that is called as technology mapping, right? So it considers what all, as I explained, the library will have input transition, output load based on the delay, right? So we have, it considers cell drive strength and area and timing characteristics before choosing it. So that is technology dependent mapping. So these are the two phases of mapping. So how does the mapping works? Mapping consideration, right? So it will select the cell based on the timing requirements. Whichever has better timing, it is going to select that, right? And drive strength for loads, because we have a load constraints there, right? And multi-drive optimization for fan out management. How you are going to manage if you have thousands of fan out, right? And Boolean matching for efficient implementation. I can change the Boolean logic from a mux to flop, flop to mux, or any SOP to POS to achieve this, right? And resource sharing for area efficiency. Suppose I have a two set of logic in two different modules, I can put together and form a single logic, so that will save my area. So I'm going to use that thing. So these are all the mapping consideration which will be used, right? So the command, right? The command is basically called a syn generic. So what we call is definition before. The first phase of mapping is called syn generic. So where basically the tool maps technology independent. So just the command is just syn generic, right? Syn generic, and it has a switch called physical, right? Which means you do, so instead of logical, it will consider the physical area while doing the optimization. That is what the hyphen physical is suggesting here, right? So what happens inside? So syn generic, what happens? We already saw that it's a Boolean logic minimization, right? And whatever the arithmetic operation you have, addition, subtraction, is going to infer that, and resource sharing and data path extraction optimization. And if there is a finite state machine, it is going to encode that and address that as well, right? And what are the benefits of this syn generic? So what is the benefit? So it creates a optimal generic netlist. So whatever the output of this is still a netlist, right? Netlist is gate level, but it is technology independent netlist, right? So this is purely focused on logic efficiency, just with the logic efficiency and not the library dependencies. That is the syn generic. So syn map is the second one where you actually do with the technology library. The same command. The command is same, syn map hyphen generic. Syn underscore generic is a previous command. Now it is going to be syn map, right? So altogether syn opt, if you do, it will do the entire three steps within itself. So there are three commands: syn generic, syn map, syn opt, right? Generic library, technology library, optimization. So when you give syn opt directly, it will automatically do all these three together. That is an advantage here, right? So mapping strategies. What are the mapping strategies here? So we have area mapping, we have speed mapping, we have balanced mapping. So based on the PPA requirements of the chip which you are going to design, it is going to map, right? Sorry. Right. So we'll go to opt command, right? So optimization strategies, as I mentioned earlier, right? So you have a lot of optimization methodologies here. How do you go? How are you going to map, area optimization? How do you going to do the timing optimization by reducing the sum of products and products of this thing? Utilize K-map or Queen-McCluskey. All those algorithms will be applied using inside the SynOpt, and because solving a one single equation is easy, we can just put it in the notebook. But when you look at the design, actual designs, it's going to have multiple levels of hierarchies and millions of gates. So how the tool does, it will just go each window and apply parallel work and try to optimize first, and then it will come up one hierarchy and do, and then one up hierarchy and again do the optimization. So it's a repetitive process, right? So that's why they say two processes are here. One is initial optimization, another one is spatial optimization, right? The first pass optimization, it's just to improve the quality of results, right? And spatial is basically when you consider the layout and then do the synthesis, it will be even more better, because you are considering the physical design aspect also. So that is spatial. We look at the spatial more when we talk about the PD, right? Next one is basically the incremental optimization. So incremental is Normal synopt will work fine, but then you do some test patterns or something DFT related things after this, and then you need to re-optimize it and make sure timing is clean. You do the incremental options, right? So synopt spatial, and synopt incremental are the commands for optimization. So they work on timing driven, power driven, and area driven, as I talked before, right? So clock tree, I'll move later. It's not for here. So remaining important things, that power optimization techniques. So as I said, some of the designs are for low power, right? So why do we need low power? Because I need to have better efficiency with using less power, because I'm going to go green, let's say. So for that purpose, they have some technologies which is implemented. So the one such thing is called as clock gating. So how many of you are familiar with clock gating? Clock gating. So I see some hand going up. You guys, clock gating. So clock gating is very simple, right? So I'll explain you to you guys. So let's say clock will be 75% of the power consuming in any chip design, right? So what is clock gating here? So in a simple example, right? Let's say in the same designs, right? You have some modules here, some modules here, some modules here, some modules here, right? And I'm going to know that, hey, this particular module is not going to work all the time, right? It's just going to work for, let's say this, if chip is on, it's just going to work for 10 minutes, whereas other chips will work for like 80 minutes or something, right? So if it is just going to work for 10 minutes, then what I'm going to do is I'm going to shut this off, right? I'm not going to supply clock for this. After 10 minutes, I'll just shut this off, shut the clock off for this particular module, right? So how do I do this? Simple AND gate, right? You know the function of AND gate? Both one, then only the output is one, right? So I'm going to have an enable signal. I'm going to attach this clock, whatever is coming here. So what happens here? So when enable is 1, clock will propagate. When enable is 0, output is always 0, right? So this is the advantage. What is the advantage here? So when I do this, let's say you have 25%, 25, right? Let's say all 4 modules have 25% components in it. So when I do the clock gating for this module, I'm going to set 25% of the power, right? So that is straight away that. But what is the issue you see here in this? Anybody can guess what is the issue here? What will happen probably? Any guess if I use an AND gate? So let's be clear to draw a waveform, right? Let's say my clock is coming like this, right? So and let's say my enable is randomly like this, right? What will happen to the output of the AND gate? Whatever here enable is high, the clock will follow, right? And what will happen here? The clock will be glitch, right? The actual, there is this AND gate is a glitch prone device. So some point of time, you cannot control the clock period here. So normal AND gate based clock gating is a glitch introducing circuit. So we may need to take care of this while addressing the design issues. So they have another proposal called as latch based clock gating, right? So when you use an inverted latch and corresponding to AND gate, use the AND gate along with an inverted latch, you will never have this glitch issues, right? So I'll leave it to you to study on that. You can come back to me any questions tomorrow, right? Study about this integrated latch and the normal gate. What is the difference? What is the advantage and disadvantage, right? So that is about the low power. So I'll get to the circuit. Right. So clock gating. So how do you enable clock gating? So I need to enable clock gating for certain modules. Tool will automatically find it. So you just need to give this command called set db lp is low power, insert clock gating true. If you just do this, clock gating will be automatically enabled in the tool while doing synthesis, right? Next one is multi VTH optimization. So what is multi VTH here? So what is a threshold voltage? Anybody can answer? Have you heard of the term threshold voltage? Correct. So threshold voltage is a minimum voltage which is required to turn on any transistor, correct? So you all know that the variation in threshold voltage can affect the delay of the circuit, right? So they took an advantage of this. So what is advantage? So if you do a cross section of an NMOS or PMOS, right, you will have a P substrate here. The substrate will be always connected to the VDD, right? So there will be a bias voltage, something called. So that we call it as threshold voltage, right? So what happens is when we increase the threshold voltage, when we use high voltage, like high threshold voltage device, what happens is your power consumption has become very, very less, right? Which means why it is coming like that, because you are going to use the substrate voltage instead of a main voltage, so the consumption of power will be very less. But what happens, what is the other side of it? Your time, which means your performance will come down. So when you use a high VT device, it is good for power but bad for timing. Similarly, when you use low VT device, it is good for timing performance whereas bad for power, right? So the multi VTH optimization, how they use is for critical paths. If you have some timing paths are very critical, so they use the low voltage LVT. So LVT means they don't bother about the power for that critical paths. But for all other paths, they can use a standard VT, which is SVT, in between the HVT and LVT, right? And they use the HVT for non-critical paths. By this way, we need to do the trade-off, right? So here, you can specify that. Let's say your leakage power you wanted to optimize. You tell the tool that set dB leakage power effort high. When you put this tool tries to use more number of HVTs, right, without affecting the timing, and then try to reduce the power. So that is the multi-VTH. Operand isolation, we'll ignore now. It's a very complex system. We need to understand low power. So I'll ignore that for now, right? Area optimization, pretty simple. As you all know, it's just a single command that set max area, give some area number and set area effort high. If you do that, you will obviously, synopt area will take care of area optimization. Try to reduce the area as much as it can, right? It can do cell downsizing, logic restructuring, etc. or anything, right? So that is on the area optimization. And finally, the timing closure, right? We do the check for the timing, what is the setup and what is the hold time violations. We do analyze timing. So analyze timing violations is basically you do report timing and see how many number of, let's say hyphen max paths. Here you can see hyphen max paths, slack lesser than 0. Slack is whoever is violating. Below 0 means it's violating, right? So whoever is less than 0, I'm going to report that path and understand why it is causing the violation. I need to fix them and redo the synthesis by synopt incremental effort high, right? And we need to give what is a target optimization. You can use size cell or you can use insert buffer. You can use any command for this purpose, right? And again, do the report timing summary, all violators, compare and make sure that timing is clean, right? So meeting setup and hold requirements is critical for timing. And one more important stuff is basically the design rule check integration. What is design rule check? So as I said, everything will have input trans and output load, right? Based on the delay is calculated. So we need to, DRC consists of two major things. One is max transition violation, max capacitance violation. So max transition means you have a limit of transition given as 0.1 in the beginning in the constraint. So whichever is going above 0.1, let's say your 0.1 is this. Let's say my design is going 0.2, 0.3, which means your rise time and fall time is very bad, right? What happens to that? Your data will be very, very much small, right? It will be active at one for a very small period of time. You should not allow that. It will again be a functional failure. So the transition limit should not be crossed. So the max transition, you will see the violation that if something is above 100 picosecond, you need to fix that. Similarly, max capacitance also. So they are called as DRC, timing DRCs. So design rule check integration, right? You can check through report constraint. It will give you all the list of violations. You need to analyze that and fix it, right? So how do you fix it? You basically fix set dB design. You give the limit of max transition 0.5, max capacitance 0.3. This is again from industry, like process guys. They'll give you that guidelines. You need to just code that guidelines as a command, right? And do synopt incremental. The tool will be able to fix the timing DRCs, right? And that's it. So report, how do you report area? How do you report QR? It's already pretty simple. Report area will give report area, and report gates will give report how many number of cells in the design, and report power will give leakage power, dynamic power, static power, right? And QR is quality of results, complete set, what the design has, how much area, how much VT type and everything, right? The comprehensive QR showing everything will get a complete picture of how the synthesis will be. Okay. And finally, once everything is clean, what do you do? So we started with read HDL, right? So we do with write HDL now, and then write out the gate level netlist, which needs to be taken to PD, physical design, right? So write HDL, whatever is mapped. When you want to write the mapped stage, you need to give hyphen switch mapped, right? And then you write it out, right? Additional outputs, what all you can write? You can write the timing constraints, and you can write the script, whatever the script used for designing doing the synthesis, right? And the SDF is nothing but standard delay format, so it's basically an RC factor used for GLS, gate level simulations. So for now you can ignore that, but whatever the additional, all the write commands is used, right? So, and script automation, right? So when you put together all these command in a single script, right, so that is going to be your synthesis script. So you just need to open the Genus tool and start from beginning, like what is the setup session, right, and what is the constraints, and how to read and elaborate, and then constraints, the synthesis, reporting, output. So all these put together, you do an automated script, so you can run it multiple times. So you start with the smaller designs, you can easily get through the complete thing and understand each and every command. Just by putting man and command name, you can get a complete help of what the command is doing, right? So advanced scripting techniques and error handling, I'll skip for now, because first you need to understand what is scripting and how it is useful in synthesis, right? So I'll just skip it. I just put it here. I'll share it with you later on how this helps, right? Once you guys complete the module of the synthesis, any blocks, right? So last, or some slides is what are the common synthesis issues and debugging strategies, right? So obviously you will have timing violations. If you have latches or something, you need to take care of that. Latch, you need to take care and you need to remove that. And timing violations, you need to add pipeline stages, or you need to do optimization in a better way to address the timing infuse. And if you have any high fan out or transition, you need to fix that. And these are the predominant common issues and debugging strategies which you need to follow to make sure that the timing is clean, right? So the best practices, right, and the next steps for implementation. So you need to do basically multiple PVT corners. As I said that we work on 200 corners, right? Because you should not just do one corner and make sure your timing is clean. You need to make sure multiple PVT corners and timing should be clean. And incremental synthesis helps for faster iterations. You do multiple times iteration, it will do a different way. It will help you, right? And you should maintain a proper constraint file, right? Every time you should not change it. You should maintain a proper file. And the log file and the report file needs to be checked each and every run to make sure there are no errors and warnings, right? And on the script development, so we need to do a common script, like a modular parametric script, so that we can reuse it for any design. So once you create a script, any RTL you give, it should do the synthesis. So that's how the industry works. So you need to do the script development in such a way that, so implement comprehensive error checking and logging. So you have a something framework of, hey, my log is this. You just, if you guys worked on Unix or Linux, you would have used egrep or grep command, right? To just grep what is the error, how do you tabulate, how do you address this, right? And make files is basically one of the very good utility to generate a flow, right? And document all non-standard settings and overrides. So what we need to use, if you are overriding any other default step, we need to document that, and we need to send this to the designer to make sure this is okay or not, right? So next step is basically we check the logic error connection. I missed that steps here. So we do the logic error correction, which we're going to see shortly. What is logic error? And then take this netlist to VLSI flow on the physical design, timing closure, verification, and sign off, right? So this is the complete flow. And basically the quote, I liked it. So this is AI generated, not mine. So mastering of synthesis is the foundation of successful ASIC design. So if you are able to master the synthesis, right, so you can basically master the entire physical design and timing analysis very well, like the timing concept and area and all these concepts, if you are familiar, right? So basically you can easily get through the other stages easily, right? So I'll stop here and we'll take care of that. I'll try to set up the workshop, like the tools, and we'll try to invoke that and see. But any questions? So we'll have some 5-10 minutes for any questions. Sorry, if it is too fast, you can let me know. Or if it is okay, also let me know. Any questions? So it's automated now. So the industry is like, see, the run will run automatically. For example, I have 200 corners in my design. There is a flow to run the 200 corners, but there is no, each and every 200 corners you need to analyze the reports and make sure it is clean. The flow will run the analysis. No issues on that. But if say in 200 corners you have like 15 to 20 corners, there are violations, and each corner can have thousands of violations, that you need to do it, how to fix it. So for that only we have scripting, like you need to know Python, Perl, and this thing you need to be familiar with that, so that you can process those report and get a unified thing, and then you can analyze. That's how the industry is working on. So Python and Perl is very important to basically analyze these reports. Yeah. So input delay is a general criteria is, suppose full chip you are working, the architect will tell you like, hey, I have this output, it is going to this portion. So you use 60% of your clock. So that is the thing they give you. If they don't give you, we can always use 60/40, which means you always consider that 60% of the delay is outside, 40% is inside. So that is a general rule in the industries. So architect and other process guys will give you that. So we don't need to worry on, that who will give. So if they don't give, we need to use this 60/40. Any more questions? Can you come again? So you are saying that Vivado, the same code is able to do it, but whereas you're in ASIC. So ASIC in the sense, which tool you used it? Genus only? It should not be that. What error you are getting? It should not happen. Suppose if it is just the Verilog code which you are using as an input, so you should not get the issue. You should pass. The output of Vivado, you should not use it in synthesis. Whatever the input you are giving as just the Verilog code, the same input you need to give in the genus. We can put it, no issues. We should not have loops actually. There is some concept called combinational loops. So you have an AND gate, an OR gate, and some XOR gate coming back to an AR gate. Let's say there is no sequential element that cannot be understood by synthesis. You will get error. You will get, there are loops in the design. It will try to break the loop by itself. But if it is not, it will report that I cannot break this loop, so you should not have this. You need to correct your design. So they are called as combinational loops. But otherwise, you should get through it. There should be no issues unless it is a Verilog or VHDL. So RAM, so if you are talking about memory, right? So there is a separate entity for that. So we should not use here. There will be something called as memory compiler. So we need to use memory compiler to understand the memory, and the memory compiler will generate a .lib. We will use the .lib here instead of a direct memory code. So memory should be done separately. We cannot do that in a traditional synthesis flow. They have some memory compiler. We need to go through that memory compiler process and then generate .lib, and that .lib is provided to the synthesis. So the .lib will have all the timing informations, how the memories, each bit is there, and the timing information is taken through all the stages. So it will be kind of a macro. Memory will be a macro. So memory compiler used to generate this. So they come under the custom design, full custom design, memory compiler, memory design actually. If it is a part of digital code, it cannot synthesize. So the synthesis, that's what I said, the constructs, right? I talked about the construct initially. Only the synthesizable construct need to be used in the RTL. If it is not, it cannot synthesize. The tool cannot, the tool doesn't have capability to synthesize memory things. So we need to separate that memory as a separate module. And instead of that, let the reference be there. Module can be there, memory module, but it can be referenced through a library itself. So if you give the memory library, tool will say that, hey, my top is inferring a memory module here, and the memory module, I see a library here, so I'm going to take the functionality from the library and use this here. So that's how the flow works. So you need to separate memory. You should not use the memory along with any other things within the same RTL code. So that's one of the RTL things which we need to take care of. Okay, any more questions? Okay, so let's take a break for 10 minutes. So I know you guys are tired, right? I'll try to set up meanwhile the genus one basic counter flow, and we'll see how we can take through this. Okay, thank you guys.